The parametric equation of a line is x of t equals at plus b and y of t equals ct plus d. To convert the equation into a rectangular form, we solve for t and substitute it into one of the equations of the parametric equation. We will use x of t to solve for t. X equals at plus b. Subtract b from both sides, and that gives us x minus b equals at. Divide a out on both sides, and that gives us t equals x minus b over a. Substituting it into the parametric equation for y, we get y equals c times x minus b over a plus d. Distribute c into the parentheses, and that gives us cx minus bc over a plus d. By multiplying d by a over a to give us a fraction that we can add into, we get cx minus bc over a plus ad over a. And that gives us cx minus bc plus ad by rearranging the order of the fractions and isolating for the fraction containing x. That gives us c over a times x plus ad minus bc over a. And that follows the formula of a line, which is y equals mx plus b. C over a is the slope, x is the independent variable, and ad minus bc is the y-intercept. Here's an example of a parametric equation that passes through the line 3, 2 and negative 6, 3. We start with x. X is equal to x sub 1 plus t times x sub 2 minus x sub 1. We plug in 3 for x sub 1 and negative 6 for x sub 2, and that gives us x equals to 3 plus t times negative 6 minus 3, which is 3 minus 9t. Now we solve for y. Y is equal to y sub 1 plus t times y sub 2 minus y1, and plugging in 2 for y sub 1 and 3 for y sub 2 gives us y is equal to 2 plus t times 3 minus 2, which is equal to 2 plus t. So our parametric equations of this line is x is equal to 3 minus 9t, and y is equal to 2 plus t. The parametric equation of a circle is x of t is equal to r cosine t plus h, and y of t is equal to r sine of t plus k, where h and k are the center of the circle. In order to find the rectangular form, we solve for r. X of t is equal to r cosine t plus h. We subtract h from both sides, and that gives us x minus h is equal to r cosine of t. We divide r out from both sides, and that gives us x minus h over r is equal to cosine t. And now we square for both sides, and that gives us cosine of t, or cosine squared of t is equal to x minus h squared over r squared. Now for y is equal to y of t. Y of t is equal to r sine of t plus k. We subtract k from both sides, and that gives us y minus k is equal to r sine of t. Divide r out from both sides. Y minus k over r is equal to sine of t. Now we square both sides. Sine of squared t is equal to y minus k squared over r squared. Adding them both together, that gives us cosine squared t plus sine squared t is equal to x minus h squared over r squared plus y minus k squared over r squared. The Pythagorean identity states that cosine squared t plus sine squared t is equal to 1. And now we multiply r out to both sides, and that gives us x minus h squared plus y minus k squared is equal to r squared. Here's an example of how to find the parametric equation for a circle from the rectangular form of a circle. X minus 1 squared plus y minus 3 squared is equal to r squared. The center of the circle is 1, 3. And the point on a circle is xy. We can make a triangle by using the other point, which would be x and 3. And from this triangle, we can deduce that the adjacent side is x minus 3, the distance from x to 1, and the opposite side is y minus 3, the distance from y to 3, and the hypotenuse is the radius. cosine of theta is equal to adjacent over hypotenuse, which is equal to x minus 1 over r. We can multiply r to both sides, and that gives us x minus 1 is equal to r cosine of theta. We add 1 to both sides, and that gives us x is equal to r cosine theta plus 1. Sine of theta is equal to opposite over hypotenuse, which is equal to y minus 3 over r. We multiply r to both sides, and that gives us y minus 3 is equal to r sine of theta. And we add 3 to both sides, and that gives us y is equal to r sine of theta plus 3. So the parametric equation for this circle is x is equal to r cosine theta plus 1, and y is equal to r sine theta plus 3. Here's the parametric equation of an ellipse. X of t is equal to a cosine of t plus h, and y of t is equal to b sine of t plus k, where h and k are the center of the ellipse, and a is half the distance of the major axis, and b is half the distance of the minor axis. To solve for the rectangular form, we will first convert each equation to cosine squared and sine squared. X of t is equal to a cosine of t plus h. We subtract h from both sides, and that gives us x minus h is equal to a cosine of t. Divide a out from both sides, and that gives us x minus h over a is equal to cosine of t. Now squaring both sides, that gives us cosine squared of t is equal to x minus h squared over a squared. Now for y of t is equal to b sine of t plus k. We subtract k from both sides, and that gives us y minus k is equal to b sine of t. Divide b from both sides, and that gives us y minus k over b is equal to sine of t. And now we square both sides, and that gives us sine squared of t is equal to y minus k squared over b squared. Now we can add both equations together, and that gives us cosine squared of t plus sine squared of t is equal to x minus h squared over a squared plus y minus k squared over b squared. The Pythagorean identity states that cosine squared of t plus sine squared of t is equal to 1, so the equation of an ellipse is x minus h squared over a squared plus y minus k squared over b squared equal to 1. Here's an example for solving for the rectangular form of an ellipse when given the parametric equation of one. X is equal to 3 cosine theta and y is equal to 4 sine theta when the center of an ellipse is at its origin. Solving for cosine of theta, we divide 3 from both sides, and that gives us cosine theta is equal to x over 3. And solving for sine of theta, we divide 4 from both sides, and that gives us sine of theta is equal to y over 4. By adding the two equations together and squaring them, we get cosine squared theta plus sine squared theta is equal to x over 3 squared plus y over 4 squared. And cosine squared theta plus sine squared theta, since we know from the Pythagorean theorem or identity, is equal to 1. We get x squared over 9 plus y squared over 16 is equal to 1. And since a squared is related to the major axis, since a is under y, we know that the major axis runs along the y-axis and the minor axis runs along the x-axis. Here's the parametric equation of a hyperbola. X of t is equal to a secant t plus h, and y of t is equal to b tan t plus k, where h and k are the center of the hyperbola. To solve for the rectangular form, we need to solve for secant squared of t and tan squared of t. X of t is equal to a secant t plus h. Subtract h from both sides. X minus h is equal to a secant of t. Divide a from both sides, and we get x minus h over a equal to secant t. And we square both sides, and we get secant squared t is equal to x minus h squared over a squared. Y of t is equal to b tan of t plus k. Subtract k from both sides, and we get y minus k is equal to b tan of t. Divide b from both sides, we get y minus k over b is equal to tan of t, and then we square both sides, and we get tan of t is equal to y minus k squared over b squared. We subtract both of these from each other, both of these system equations from each other, and we get secant squared of t minus tan squared of t is equal to x minus h squared over a squared minus y minus k squared over b squared, and secant squared of t minus tan squared of t is a Pythagorean identity. We get x minus h squared over a squared minus y minus k squared over b squared is equal to 1. For graphing the parametric equation, or any parametric equation, we need to plug in values for t. But first, to find the rectangular form, we can solve for t. In this case, we use the equation of x. X is equal to t minus 4. Adding 4 to both sides, we get t is equal to x plus 4. And then the substitution for t into y, we get y is equal to x plus 4 over x plus 4 minus 4, which gives us y is equal to x plus 4 over x. For graphing the equation, we go back to the parametric equations, and we find in the y equation, when t is equal to 4, y is equal to 4 over 0, and since that cannot be true, t cannot be 4, and that is our asymptote for the x and y equations. So when t is equal to 0, x is equal to negative 4, and y is equal to 0, t is equal to 1, negative 3, y is equal to negative 1 over 3, and so on. And the left-hand side shows the plotted graph, and a domain that states that t cannot be equal to 4. The parametric equation of a parabola is x of t is equal to at plus b, and y of t is equal to ct squared plus dt plus e. In order for us to find the parametric equation, when given y is equal to 1 minus x squared, when given the following parameters, t is equal to x and t is equal to 1 minus x, we let t equal to x, and that gives us x is equal to t, and plug that into the formula for y, and that gives us y is equal to 1 minus x squared, or 1 minus t squared. Then letting t equal to 1 minus x, we obtain the parametric equation, which is x is equal to 1 minus t, and y is equal to 1 minus x squared, which is equal to 1 minus t squared, which ends up being 2t minus t squared. So the parametric equation of this parabola is x equal to 1 minus t and y equal to 2t minus t squared. We can convert these parametric equations by eliminating the parameter, starting with y. Y is equal to 3 sine of 2 theta. Sine of 2 theta is a double angle formula. Y is equal to 3 times 2 sine theta cosine theta. By squaring both sides, we get y squared is equal to 9 times 4 times sine squared theta times cosine squared theta, the Pythagorean identity. And we can replace sine squared theta with 1 minus cosine squared theta, and we get y squared is equal to 9 times 4 times 1 minus cosine squared theta times cosine squared theta. By squaring the original x equation, we get x squared is equal to cosine squared theta. We can plug in x squared for cosine squared theta, and we get y squared is equal to 36 times 1 minus x squared times x squared. We can take the square root of both sides, and that gives us y is equal to plus or minus 4x times the radical 1 minus x squared. Here's a graph of the previous equation for when theta is equal to pi by 4 or 45 degrees. When theta is equal to pi by 4, cosine theta is at 0 is 1, and it follows in each increment of pi by 4 is root 2 over 2, and so on until it finishes its revolution at 2 pi. And y is equal to 3 times sine of 2 theta, which is 2 times 45. Sine of 90 is 1. So for each increment of pi by 4, sine is 1 times 3, and that is how we graph the parametric equation of x equals to cosine theta, y is equal to 3 sine of 2 theta when theta is equal to 45 degrees. For finding the parametric equation of a cycloid, we will decipher the picture on the bottom. Let theta be the measure of the circle's rotation, and let P be a point on the edge of the circle. When theta is equal to 0, pi is at the origin. When theta is equal to pi, point P is at its maximum at pi a 2a, and when theta is equal to 2 pi, P reaches the x-axis again. Solving for sine of theta. Sine of theta is equal to sine of 180 minus theta, and that is equal to sine of the angle APC. For solving for sine, because it's 180 minus theta, that makes the opposite angle, the opposite side, AC. So solving for sine, AC over A, because the hypotenuse in this case is the radius, and that is equal to BD over A. For cosine of theta is equal to 180 minus theta, and since the circle is rotating clockwise, cosine of theta is negative, and negative cosine of theta of angle APC is equal to negative AC over A. And if you can see, cosine, in this case the triangles would show anyways that cosine is negative. Now, looking back at sine of theta, we can multiply both sides by A, and that will give us BD is equal to A sine of theta. And since we know that the point P on the edge of a circle started at O, the origin, we can understand that OD is equal to the arc of PD, since the distance traveled is equal, and PD is equal to A theta. So for x, we have x is equal to OD minus BD, and plugging in the values we just solved for, we have x is equal to A theta minus A sine of theta. For y, we look back at cosine, and we multiply both sides by A, and that gives us AP is equal to negative A cosine. So solving for y, we can look at BA is equal to CD, which is the radius A. So for y is equal to A plus negative A cosine. You can factor A for both equations, and we will get the standard parametric equation for a cycloid, which is x is equal to A times theta minus sine theta, and y is equal to A times 1 minus cosine theta. For finding the standard equation of an epicycloid, let A equal the radius of the large circle and B equal the radius of the small circle. Theta is the angle of the large circle and beta will be the angle of the small circle. We can use vector summation to find the general equation of the formula. For the first equation, we will add the length of both radiuses and multiply it by the cosine and sine. So we get, for the first vector, a plus b times cosine of theta and a plus b times sine of theta. For the second vector, we will take the cosine and sine of the angles added together, and that will be cosine of beta plus theta and sine of beta plus theta. When theta and beta are equal to 0, the point on the small circle and the starting position for the large circle are equal. Whatever distance is traveled lets us know that the arc lengths are equal. So S is equal to A theta, the arc length of the large circle, and S prime is equal to B beta, the arc length of the small circle. And since we know they're equal to each other, we can solve for beta. So A theta is equal to B beta, divide B out. You get beta is equal to A theta over B. And now to solve for the parametric equations for the cycloid, we can solve for x, and x is equal to A plus B times cosine theta minus cosine A theta over B plus theta, and it's minus because of the rotation of the small circle on the large circle. And y is equal to A plus B times sine theta minus sine of A theta over B plus theta. And for both x and y, we can finalize the equation by simplifying the fraction. A theta over B plus B theta over B, factor out theta, and our final equation is x is equal to A plus B times cosine theta minus cosine of A plus B over B theta, and y is equal to A plus B times sine of theta minus sine of A plus B over B theta.